Okay, lesson 3 is all about figuring out how to use that error that we calculated last time in order to update our weights. Remember, the weights are the model. I can't say that enough. People keep still are getting that confused. These things called weights inside here are the model. And I can show you for this particular uh, one what the matrix is. These two are called our I bias, but the rest of these weights are, and we'll write the I bias too. So it's W11, W12, W21, W22, W31, and W32. Right? Those weights are the things that are in here that's going to be able to take this 3x2 matrix that we talk about down here and multiply the outputs here in order to get the inputs for that matrix, right? So again, go to the Jupyter Notebook, check that out. But just understand that these weights inside here, so this is WIH. And what we're going to do is we're going to have some values in here, and then we're going to use the gradient in order to find the delta. So we got WIH old or new is what we want to. We want to find the new, and we want to that's WIH old, just like we've been doing in the past, plus some delta WIH. And we claim that this is going to be the gradient, the negative gradient is the direction that we're going to go. All right, and that's the whole purpose of today's class, is to find that guy right there. Not only for WIH, but also for the I bias vector. I bias vector is equal to, in this case, just W01 and W01 and W02. The thing is, the stuff that we derive today will work for any size system, right? So in other words, like later on, we're going to come and we're going to make 280 input nodes, and it's going to work for that too. And I'm going to have 280 by however many hidden layers we decide to have. But you have to kind of see an example in order to figure out what's going on. And we could do the same thing for WHF and the H bias, right? So that's the other part of our model that we haven't done yet. Okay, so that's the purpose. We got to find the delta, all these deltas. That's really what is the update based on one particular input and a target, and knowing what the output comes out of the model and what the target is. We calculate the error, we back propagate it, and then we use those two errors in order to find this delta WHF and this delta bias and this delta WIH and this delta I bias. That's really, that's what we're looking for, that delta. How much are you going to change because of this input and that target? Okay, so in order to be able to do that, we got to remember, so let's recall the following. And I don't think I'm going to really write much out here because this will be a long video if I did, but just recall that the output of the input layer is equal to the input of the input layer. So really nothing goes on here, right? So whatever comes in here kind of goes out there as OI1, OI2, and OI3, right? So those things come out of there. And then the next part is, well, how do you get H, or I'm sorry, Control Z. Control Z. How do you get XH1 and XH2? How do you get these two numbers? And that's just I bias, which is W01 and W2, plus the transpose of WIH times OI, so times that vector there. And that's how you get it. It's XH, and then let me change the color. It's like we're getting, so then I got O, is that H, OH1 and OH2. Well, how do you get those two? You simply just take the sigmoid function in order to get that. Let me use pink, and then I'm going to get XF1, XF2, XF3, and XF4. How do you get those? That's just H bias, 1, 2, 3, 4, plus WHF, which is that matrix that we wrote, or we could write, transpose times OH times the thing that came out, and then you add those two together and you get XF. And then finally the output, so this part that we've already got written here, how do you get that? You just take this, remember the activation functions as sigmoid function for those. Okay, Also recall that the back propagation, so the easy one is EF, right? So I can very easily just take whatever the targets are, T1 minus OF1. That'll be the first component of that vector, of the EF vector. And then T2 minus OF2. And that'll be the second component, right? So all you do is you take the target vector, subtract the the output vector of the final layer, and bam, that's the easy part. The next part is, we saw last video that it's just the WHF matrix. This matrix is 2x4 matrix times EF, the EF vector, in order to get EH, and that will give you a semblance of the error that's associated with each one of those two nodes and the weights that are in there. Okay, so today's class is all about using EF, this first vector here, to update WHF and bias, say H bias, since I didn't write it in there, and I bias for this one. So we're going to use EF to update WHF, and we're going to use EF to update H bias. We're going to use EH, this thing that we calculate here, to update WIH, and then I bias. Let me put a vector sign over there. Okay, so here's a picture of it, forward propagation through the network to get OF, and then once you get OF, you subtract the target minus OF to get EF, and then you back propagate that thing EH using this. Okay, I mean, obviously there is no error for the input vector, so hopefully that doesn't make that does not make any sense if you can't have error in the input. All right, so here we go. Here is the math that's associated with it. So here, let me put okay, so here, I think this will work. So what is XF? All right, so what is this XF business? Well, that's just H bias plus WHF transpose OH. So that would be WO1 plus W11 OH1 plus, so all I did right now is I just wrote out the math that you would have to do. So for example, if we come here and we find XF1, all that is WO1, right? So the WO1 plus, and then W12, yeah, I got to go up here. Let's just do 2. We'll do this row. So that'll be XF2. Yeah, that's the one that was going there anyway. So that'd be XF2. So that would be WO2, which is what you got there, plus this row, W12 times OH1, which is what's coming out of that node, plus whatever this guy is, W22, right, which is that one, times whatever's coming out of that node, which is OH2. And you could do this for all, again, this is just matrix multiplication plus that vector. So this is the matrix WHF transpose, which would be W11, W21, W12, W22 times the OH vector. So again, you can kind of see the math, just the matrix algebra that's involved there. So now what I want to do is I want to take this piece and say, well, what is OF then? And I probably should put a vector sign on there. So all you need to do in order to get OF is take the sigmoid of the previous guys, right? So I'm just going to take the sigmoid of those, and you can kind of see them written there. All right, so that's what we got. And then the next question is, well, what is EF squared? Okay, so I'm going to use this because I know that EF squared is the square of each one of these components. And EF1 squared is T1 minus OF1 squared, T2 minus OF. So you can kind of see what happened. So all I did was I substituted in this what EF actually is in the calculation. So it's just target minus OF, and then I squared it. So target minus OF, what's coming out of the model, quantity squared. And you kind of do that all the way down for each component, however many output nodes that you have. And now we substitute in this thing, this is OF1, this is OF2, this is OF3. So we start substituting in, and we get T1 minus sig of XF, which we actually, I guess we could kind of jump, since I've already done this calculation, we can just jump here to the end. It's T1 minus the sig of this, that's OF, quantity squared. And the second one would be T2 minus the sigmoid of this whole thing, whatever's in that second line there, quantity squared, and so on and so forth. So now what we want to do is how do we use this information in order to find, so what we need is the partial derivative. So why did I square that? Because we don't want uh, we want negative numbers to come into play here. So we actually want to make the distance of the error as small as possible. So how do we use the gradient descent algorithm to make EF squared as small as possible? By adjusting the weight. So the point here is, well, how do you find the I guess what you're looking for is this delta WO1 and this delta WO2 and this delta WO3 and this delta WO4. How do you find those? Again, there's just the gradient. So I'm going to take the gradient or the partial derivative. Remember, the gradient is the partial derivative of the function over with respect to whatever variable that you're using, right? So in this case, WO1. In this case, it'll be W11. In this case, it'll be W21. And I put the dot that there because I didn't want to write this out for each one of these suckers. But, you know, if I was looking for W112, W13, W14, we could do 21, 22, 23, and 24 because those are all W's that are in my functions up here. All right, so where do we find these? We use the gradient descent algorithm, and we're going to let alpha be the step size, and we're going to let alpha be on each one of these suckers. So the delta WO1 is some alpha times the gradient of this EF1 squared with respect to WO1. The delta W11 is, again, this alpha times the partial derivative EF1 squared with respect to W11, and so on and so forth. So you can see that each one of these uses the EF1 squared. Well, why? If you go up here and look at EF1, this EF1 squared, kind of march over, you'll see that it has WO1 in it, W11, and W21. There are no other WO1s, W11, or W21s in the other functions. So all I need to do is take the partial derivative of this function with respect to WO1, W11, and W21, and that'll tell us how much to move each one of those suckers. All right, so what I've decided to do, and you can kind of see it in red here, is just to find delta W23, and then what we'll do is we'll put that into the matrix and kind of figure out, hopefully it'll be very straightforward so that we can figure out what to do with all the rest of the W's. That's the idea here. Okay, and so so all I'm saying here is you're going to take a bunch of chain rules, right? So I'm taking the partial of this function, of this EF3 squared function with respect to W23. And when you do that, well, you get 2 times, you know, to bring the 2 out in the front, subtract 1, you get the power rule there. And then you got the power times the derivative of the entire, so it's 2 times this times the whole thing inside, so whatever's in the inside. And then you got to take the derivative of the inside. And by doing that, you got a -1. So that goes there. And you get the sigmoid, so then it's the derivative of this one, which the derivative of this one would be the sig. Remember I'm sorry, I guess I need to remind everybody that the derivative of the sig function is just this. So it's the sig and then 1 minus the sig. So that's where you're getting the sig and then 1 minus the sig. And then the derivative of the inside, or again, another chain rule, right? So then the derivative of the inside is just with respect to W23, right? So this is the partial with respect to W23. It's just OH2, and that's where this OH2 is coming from. Whew. All right, that seems like a mouthful. Now we're going to do some simplifications. So what is T3 minus sig of all this business? So if you just go back up and look and see what we're talking about, it's T3 minus the sig of all that. So what is T3 minus the sig of all that? It's just EF3, right? So TF minus the sig of all of that is just the guy that's inside the square, which is just EF3. So in other words, it's that error EF3. It's the error of the third component in your final layer's error vector, right? So it's just that one component. And then the 2, we're going to let it go because we have alpha. We already have a constant out there. So all that 2 would make us have to do is make alpha even smaller. So we just let it go for now and just let alpha kind of suck up that 2 because there's going to be a 2 on every single one of them because I got a square on every single one of them. And then let's see, so that's EF3. How about this one? So sig of all of that business is just OF3, so that we already know what that number is. And then 1 minus the sig of all that business is also OF3, so 1 minus OF3. and then times OH2. So, and we also know what that number is. So let's put all of this garbage together. So that shit garbage. This all of this information together, and we get the partial of EF3 squared with respect to W23 is just the third component of my error of the final layer, my output of the final my third component of the output vector of my final layer, and then 1 minus that same number times OH2, which we can just pull off the values, right? So we can find this number. These are all out there, and that will give us delta W23. All right, so remember what we're trying to do here, right? This would be delta W11, this one would be delta W12, this would be delta W13, and this would be delta W23, right? And then you can fill in the blanks, right? 1, 1, 1, 2, 1, 3, 1, 4, 2, 1, 2, 2, 2, 3, 2, 4. So these, if you took these partial derivatives and did the same thing that I did here, you would find out that these values are simply kind of the same thing. So this is the one we've already done that we just did, that I'm going to substitute in. It's this EF3, OF3, 1 minus OF3 times OH2. But then if I wanted this one, well, I would just do EF1. I mean, so again, you could just take another, take another partial derivative and check that out. But it's literally going to be, so here's an easy one to do. OF, so this would be exactly the same except the last derivative, right? So the last derivative is the derivative of the inside with respect to W13, and then it's going to obviously be OH1, so that would be OH1. So that's the only difference in that derivative, or in that partial derivative. So that guy would be OH1 instead of OH2. Okay, so knowing, or kind of picking up on how this thing is, or what the pattern is for this, we see that this little matrix here is going to give me my update to WHF. So what you do is you start off with WHF, you start off with your old WHF, you add this business, this partial derivative with respect to each one of the components, and you add those two together and you get your new piece. Also, we need to update our H bias, and where H bias is equal to, again, I need to update W01. I need to update W02. I need to update W03 and O4, right? So let's just go back up and see where W01 is located. So in this function, W01 is only in EF1 squared. W02 is only in EF2 squared. W03 is only in EF3 squared, and so on and so on. I mean, you guys see what's going on here. So now when I take this partial derivative with respect to W01, 2, 3, or 4, what happens is the same thing happens, except when I get here to take the derivative. So if I'm doing W03, when I take the derivative of this inside piece here, this becomes the partial of W03 with respect to W03 is just 1. So there is no weight on there anymore. I'm sorry, there is no constant on there. So before I had an OH1 constant on there, now the constant is just 1. So this guy basically goes away, and it's just the same business except no OH whatever. So in this case, it looks exactly, so in other words, this guy looks exactly the same. So let me draw that. It looks exactly the same as that one, except there is no OH business on it. I can't get that straight. Okay, so there is no OH piece on there, and that would be the same for each one of these. So instead of, just get rid of the OH, and that becomes that one, and this right here without the OH becomes that one, and so on and so forth. So the deal here is if you calculate H bias for this delta H bias first, we can use that delta H bias in order to calculate the the delta WHF. And let me show you how to do that. From linear algebra, remember the rank, I don't know, you guys probably don't remember, but there's this thing called a rank 1 matrix. What it does is if you put two vectors in a certain order, you produce what's called a rank 1, and that's what this thing is. It's going to be a rank 1 matrix. So what we'll do is we'll put the OHs, the things that we want to be on the top and the bottom in the rows, OH1 on that row and OH2 in that row, and you put those as a column vector, and then you multiply that, so that's a 2 by 1, and then I'm taking this thing that I just calculated over here for the H bias. So basically just, if this is H bias is a column vector, just turn it into a row vector, and then multiply those two together this way, in this fashion. So realize that's a 1. Yeah, that's not right. That's a 1 by 4. Sorry. Let me rewrite that. That is a 1 by 4. And what happens is, because that's a 1 by 4, then you're going to end up with a 2 by 4 matrix. And that 2 by 4 matrix is going to have, each one of the rows is going to have an OH1 on it. And then each one of the second rows will have an OH2 on it. So that's what that'll look like. And it's exactly what we're looking for up here. Okay. And so it says calculate the delta H bias first and then use it to calculate WHF. Okay, so that's exactly what I just got finished saying. And then if you use the same derivation, so remember what we're doing is we're going backwards and we're using EH squared for this next piece instead of EF squared. And if you did that, if you did all the partial derivatives and whatnot, you would find out that I bias actually looks very similar to the other one. The delta H bias, let's see if I can put these on the same screen. Here, I can at least put this one on there. Whereas instead of the EF1, this is now EH1, and instead of OF1, it's OH1, and 1 minus OH1 is okay, so you can kind of see what's going on there. And then did the same thing with WIH. Instead of these being OHs, they're obviously OIs, and you did the same business with the rank 1 matrix. You would get a 3 by 2, which is exactly what we need for WIH to work. Okay, so get ready, because we're going to program all of this stuff in the next video. So I'm just going to jump back and forth, program. I don't know if I'm going to program the error in the video. Yeah, I guess I will. I'll program the error in the video, and then we can possibly do it in class as well. Okay, that's all I got. Hopefully you guys got some out of this one, and we will, it's probably very long. I apologize, but there was a lot in this one. See ya.